Hello dear students. So in this particular video we are going to discuss about the problem solving in AI. Exactly what is the meaning of problem and how we can solve the problem in a artificial intelligence. We'll discuss that particular in this particular video. So let's see, first of all, if we're talking about problem solving, so simply problem is what? It may be any real world problem. It may be any statement that we want to solve and we want to give an output corresponding to that particular. Okay, so steps to build a system, a particular system to solve a particular problem. So first of all, you need to do one thing. You need to define the problem. Okay, so first thing is what? First of all, you need to define the problem. What exactly the problem? What is the definition of that particular problem? You need to give that particular thing. Okay, so specify the initial situation and define what final situations are acceptable solution. Means you need to specify what would be the initial situation, what would be the final situation, and what exactly the final outcome that you want. Okay, means that would be the problem statement. We want to solve that problem statement. So what would be the current situation? What would be the final situation? We need to give each and every clear specification about the problem definition. Okay, after then what to do? We need to analyze the problem. Okay, analyze the problem carefully, since the effect which techniques are most suitable for solving it. Definitely, if you are having a problem, it may possible there exist multiple ways, multiple methods to solve that particular problem. You need to analyze the problem very carefully, and then you need to choose the problem solving technique. So the problem solving technique should be what we can say effective, best to solve that particular problem. Okay, so for that you need to analyze the problem statement also. Isolate and represent. Identify and represent the knowledge required to solve the problem. Definitely, when you want to solve a particular problem, definitely you need a certain knowledge to solve that particular problem. So you need to identify as well as you need to represent the knowledge that is required to solve a particular problem statement. At the end, the selection. Choose the best technique for solving the particular problem. So at the last, now you need to choose which technique is best to solve that particular problem. So ultimately we can say that we need to follow the following 4 steps. First of all, we need to define the problem. We need to analyze the problem. We need to isolate and represent the knowledge, as well as we need to choose the correct selection technique to solve that particular problem. That would be the steps that we need to perform. So simply, the definition for problem solving is what? Problem solving is a process of generating solutions from the observed data. Okay, in the past you observed some data, you are going to use that observed data, to solve that particular problem. Okay, so that would be the problem solving. Now see, the next term that comes in our mind is what is state and what is state space representation. So if we are talking about the AI, so especially in a problem solving, represent a problem in the term of state as well as state space. It helps a computer system to a systematic search for a particular solution. Like suppose you are having one particular problem, then definitely there is a initial state of that problem. Okay, as well as there is some final state, or we can say that a goal state of that particular problem. What we want? We need to apply a systematic rules, systematic ways, systematic knowledge to go from initial state to the goal state. So from initial state to reach the goal state, there are so many intermediate states. So this all are states. Now how we can go from initial to goal? So for that we need to make a diagram, we need to make a state space chart. Okay, so that is the ultimate point. Got it? Now see here, when someone asked you what is a state, so state is what? It represents a snapshot or description of the system at a particular point of time. Means if you want to solve a particular problem, let us take an example of a puzzle problem. Okay, I am having a 8 puzzle problem. Okay, and there is some initial situation that gives to you and you need to convert that puzzle to the final destination or final result. Okay, so state is going to represent a snapshot description or a particular, at a particular point of time, how your system is look like. That would be the state. It include all information necessary to describe the current situation of a problem. Okay, let us take an example. 8 puzzle problem. A state is arrangement of 8 tiles and the blank tile space. In chess game, a state is the current configuration of all pieces on the chess board. Like initially, what we can say, initial arrangement on a chess board is somehow like that. Total 16. What we can say, 8 cross 8 chess board is there, and all the pieces are arranged in a systematic way. After that, you are performing certain moves. After every move, we can say that there is one of the state. Okay, and at the end there is a goal state, means one of the player is winner. That would be the goal state. In the route finding problem, a state may represent the current location, like CTA. Let's say I will give you an example for 8 puzzle problem. Okay, supposed to be you can see here, like suppose I am having one 3 cross 3 tile. Okay, and I am having a goal state. What is a goal state? You can see 1 2 3 4 5 6 7 8, means the arrangement of tile is somehow like that. That would be the perfect 1 2 3 4 5 6 7 8 and the blank tile at the last. Supposed to be the given tile is somehow look like this. Now what we want, we need to, that is the initial state. Initial state. So can we say that this is not a systematic arrangement? That would be the systematic arrangement. So we want to go from this initial state to that particular final state. Okay, this is one of the state. Now what we can do, so there is a blank tile, so a particular blank tile can move up, left, down, right, like that, and there are different actions. We need to perform action, like it might be possible I am going to move this on left, or I am going to move this on right, or I am going to move this on down. I can do anything. So there are different states. Out of them, one state may reach your final goal earlier, some state may reach your final goal later. We need to find out what is the minimum number of moves or what is the minimum number of states that we need to change to reach from initial to final. Okay, so as it in this particular current scenario, what we can say, there are 3 different moves that we can perform. Either we can go like this, this, or down. Okay, like that. So we need to perform a move corresponding to that blank tile, and we need to arrange this. Okay, all moves are corresponding to a blank tile, nothing else. Now see, so the point that I told you, initial state, this is a starting point of a problem from where we need to start the searching, or from where we need to start the solving a problem. Goal state, that would be the desired or final state where we need to stop. Okay, and we need to achieve that particular goal state. Now there are certain operations. Operations are rule or action that can be changed one state to another. Like for 8 puzzle problem, the tile can move left, right, up and down. We can do this 4 thing. So these are the operations, the point that I told you. Now a state space. So a state space is the set of all possible states that can be reached from the initial state by applying operations repeatedly. We are going to represent that in the form of nodes and edges. Okay, node represents a state and edges represents action. Okay, the transition, when this transition is going to perform. So let's see. Suppose if we are talking about this one, so here what we can say, suppose that would be a node. So now we can perform 3 different moves. We can we can go to this tile can go to the left, right and down. If it goes to the left, then it look like 1 3 4 2 6 7 5 8. Here what we can say, if it moves to the right, so 1 3 4 2 6 7 5 8. If it is going to move to the down, then what we can say, 1 2 3 4 6 7 5 8. It look like this. Okay, now we can explore this one also, we can explore this one also, we can explore this one also, and similarly we need to explore each and every state. So that complete diagram is a state space diagram. Out of them, some moves are definitely wrong, some moves are correct, some moves reach destination earlier, some moves reach destination later, some moves might be possible goes in a looping. Okay, so there are different what we can say states, and there is a different representation corresponding to each and every state. We need to choose, we need to apply some techniques to identify or to reach the goal state earlier. Definitely we need to expand each and every one. We can use different type of techniques. We can apply BFS, we can apply DFS, we can apply like a star algorithm, we can apply branch and bound technique. There are so many techniques that we can apply. We will discuss that later on with what are the different type of techniques and which technique is best. We will discuss this all things. But as of now, this is the state, this is the another states, and we need to continue like that until we got the go to the goal state. So these are the different type of states, and the complete diagram is a state space diagram, and this arcs represent, this transition represents the action that we are going to perform. Okay. So a state space representation, it is a formal model, defines the initial state, the set of operation, the goal state and the path cost. Okay, path, why we are going to calculate path cost? For the optimization. Like supposed to be one path is very longer, you can reach the goal state. One path is smaller, and with the help of that you can also reach the goal state. So which path we need to choose? The smaller one. So formally what we can say, a problem can be represented as a state space search in which you need to mention a state space, initial state, operation, goal state and path cost. You can see the representation is look like that. This node represents the initial state, the problem that is given to you. Okay, now there are certain intermediate states, and at one specific point you can reach the goal state. Got it? Let's see, for the previous problem, if I will if I am trying to solve, so let's see what would be the solution. Like that. Okay, so as you can see there are different moves, but supposed to be I am going to choose the down move. 1 3 4 6 7 5 8. Now if I am going to choose the, here is down, now again down. So 1 2 3 4 5 6 7 8. Now choose right. So 1 2 3 4 5 6 7 8. That would be your goal. So we need to perform down down right, like that. So like that we can solve this particular problem. But definitely in a state space we need to explore all the states, and then we need to check that. Definitely there is some bounding algorithms also. You can bound the branches, or you can find out the list cost, which node gives you or which state gives you list cost. You need to explore only that state, no need to explore the remaining states. Like that you can observe that by using the goal, like that would be the goal. Initially how many tiles are, they are not at actual places. So you can see here 2 is not in actual places. 1 2 3 4 5 6 7 8 9. So these three tiles are not there at their actual location. After performing down, up and left different type of moves, now check that how many tiles are not at their actual location. If the number of tiles are going to increase, that means we are not going to explore that particular node. If the number of tiles they are not at their actual location is going to decrease, then you can explore that particular node, like in this situation. Now we can say that only 2 tiles are not at their actual location. Here only 1 tiles is not at their actual location. Here all tiles are at their actual location. So that is the way. List cost. Got it? Now let's talk about agent knowledge representation. Like, if we are having a knowledge to solve a particular problem, so how our knowledge is going to represent, or how we can represent our knowledge, that is called agent knowledge representation. Okay, so an agent in AI needed knowledge about the environment to make intelligent decision. Definitely, supposed to be I am going to solve a particular problem, so we can say that I am an agent. Okay, so agent should have a knowledge about the environment to make intelligent decision. Like, I want to solve a particular problem, so definitely I should have a knowledge about how we can solve that particular problem, or how I can solve that particular problem. Then I can easily solve the problem. But if I am not having a knowledge, then how I can solve problem? I can't solve problem. Now I am having a knowledge, but the representation of knowledge is also compulsory, because we are training the system, we are training the model. So inside a model we are going to make one agent, and that agent has a knowledge, and that agent want to represent its knowledge. So agent representation, knowledge representation, is the way this information is stored and structured inside the agent, so it can reason, learn and act effectively. Definitely, you are having a knowledge, you need to specify, you need to represent your knowledge in some structured way, or you need to store that, so we can learn from that knowledge, we can act according to on that particular knowledge, and on that we can perform certain work. There are different type of knowledge representation. You can represent your knowledge as a atomic representation. You can represent your knowledge using propositional state representation, true, false. Relational state representation is also possible. First order representation is also possible. So these all are the different ways with the help of that you can represent your knowledge. Okay, now let's see, we'll discuss the first one. Now see, the first is atomic state representation. Okay, let's see, the first is atomic representation. In atomic representation, each state of the world is treated as a single individual unit, that is called a atom. Okay, now the agent does not know anything about the internal structure of a state. Okay, means agent is not knowing anything about what is the internal structure of that particular state. Okay, in which what we are treating each state as a single individual entity, that is a atom. Means we can't break that state. You can take an example like in a maze, each cell is a separate atomic state, The agent only know it can move from one cell to another without knowing what's inside a cell. Classical search algorithm like BFS, DFS, A star uses atomic search representation. Like in breadth first search, you are at a particular node. Suppose you want to go to a destination node, but you don't have any information how you can go to that particular node. What you need to do, you need to start from this particular node and you need to explore which node is connected to that node. Now you need to go to that particular nodes. Then you need to explore that node. Then you need to explore that node. And at the end, either you can reach the final state or might be possible it is unreachable. So whatever will be the result, you got that later. But at the beginning, you are not having a knowledge about how to reach to the destination, but you know the procedure. If I want to go somewhere, so first of all, I need to go to the node that is connected to me. And then I need to explore that node. And then I need to explore that node. At the end, I can reach the destination like that. Okay. So the classic algorithms are, we can say that they are going to use the atomic state representation. Now see, propositional statement representation. Propositional statement representation means what? Simply we can say that each state is represented by a set of propositions. Like we can say that fact. Proposition means a statement is always either true or false. Okay. So the agent representation knowledge in a logical form using propositional logic. Like you can see here, I am using a function like at home, and second function has umbrella. If at home is true and has umbrella is false, what is the concluding meaning of this? The agent is at home because it is true. So the agent is at home, but it does not has umbrella. Okay. So logic based reasoning, truth table, inference systems that we are going to use. Like there is one statement P. Today is raining. And a statement Q. Today is Sunday. And if I am writing P and Q, means what we can say? Statement P is true as well as the statement Q is true. If we are taking AND operation between them, means both are true. Means today is raining as well as Sunday. If I am writing negation P and Q, means the first statement is false and second statement is true. Means today is not raining, but today is Sunday. If I am writing negation P or Q, means what? Either this statement is going to true or that statement is going to true. So either today is Sunday or today is not raining, or we can say that either today is not raining or today is Sunday, like that. So what we can say, we can specify our knowledge in the form of logics, in the form of truth tables. Okay. So each and every statement is either true or false, and we can use different type of operations between them. Okay. So that is a representation of knowledge using propositional states. Okay. So this is a kind of representation of knowledge. Means first statement is going to represent at home is true, and second represents has umbrella is false. Okay. Let's see the next one. Relational statement representation means there is a function and we are passing multiple argument between them, and that is going to represent a knowledge. You can see an example here like this. This is more expressive as compared to the propositional logic. Okay. On box table means box on table, that would be the first statement. Second, ball inside box. So X and Y representation. So a box on a table and ball inside a box. Generally, relational state representation is used when you want to represent your knowledge with the help of graph, you want to represent semantic networks, or you want to use in a planning systems. So at that place you can use this on. Now, first order predicate logic. First order predicate logic. You can see that. That is the most powerful, and we can say that the general form of representation in which what we are doing, you can see here. See, This is the first order predicate logic. What we are doing? There's a relationship parent Ankush Kush. So Ankush is parent of Kush. X is parent of Y. Parent Ankush love. Ankush is parent of love. Father XY tends to parent XY. Means if X is father of Y, that means X is parent of Y. Okay. Parent XY tends to ancestor XY. If X is parent of Y, definitely X is ancestor of Y. Now here, if X is parent of Z, Z is ancestor of Y, then X is ancestor of Y. That would be the, means if these two conditions are going to satisfy, then this condition is going to satisfy. Now, what is exactly the meaning of this? First two statements are going to represent Ankush is parent of Kush and love. Okay. Next statement is representing that every father is a parent. This statement we can say that if X is parent of Y, if X is father of Y, X is parent of Y, and if this statement is true for all X, so what we can say, every father is parent. A parent is also ancestor. That would be the next line. And the last one says that if a person is parent of someone who is ancestor of another, then the first is also the ancestor of the last. Like grandfather relationship, X is parent of Z. Suppose Ram is parent of Raj, and Raj is ancestor of Ravi. That means Ram is ancestor of Ravi, like that. So that is the representation of knowledge using first order predicate logic. That is most powerful way to represent your knowledge. So whenever an agent want to represent its knowledge, it can use any one of them to represent the knowledge. But the fourth one, the last one, is very important and most powerful technique. Let's see an example of classroom or a student example. Like what we can conclude with the help of this. If X is a student, X attends class, and this condition is true for all students. So all students are attending class. Teacher Mamta, means what? Mamta is a teacher, and Mamta teaches what? Class. So Mamta is a teacher who teaches that class. Neha is a student, and Neha is attending that class. Okay. So from this, what we can conclude? So we can conclude that simply Mamta is a teacher of a class, Neha is a student of a class, and every student is going to attend a particular class. If we are talking about the Neha is going to attend a class, like that. Okay. Let's see one problem statement. Just read this problem statement, and we want to solve that particular problem statement. So what would be the solution for this, or how we can make a solution for that particular? So this is a classical jug problem. You are given two jugs. Okay. What? We are given two jugs. A jug 4 gallon, supposed to be, this is X, and another jug 3 gallon, this is Y. Okay. A pump has unlimited water which can use to fill the jugs and the ground on which water may be poured. Means you can fill jug any number of time. You can pour the water on ground any number of time. There is no issue. What is the main point? There is no marking on a jug, and what we want to fill 4 gallon jug exactly 2 gallon. Okay. So initially what we can say, initially you are having a solution XY, that is what? 0 0, means both jugs are empty. That is initial state. And what is our target? Our target state is what? 2 0, means X 4 gallon jug should be filled 2 and the another one is 0. That would be our goal. And we are not having any marking on jugs. Now what is the minimum number of moves that we can reach to the goal state? What is the number of moves required? Let's see. We can do one thing. We are at 0 0. First of all, I will do one thing. I am going to fill the first jug. So it's 4 0. Now I am going to fill the second jug. I'm going to fill the second jug. So it's 4,3. Initially both jugs are empty. I'm going to fill the first jug completely, 4, 0. Now I'm going to fill the second jug, so it becomes 4, 3. Okay. Now what I can do here, I can perform some operations. I need to perform the sum operations, like that I can reach the destination goal earlier. Okay. So like you can empty this jug, you can send this 3-gallon water into the second one, like that. There are multiple ways. Okay, but we need to find out the smallest way or the minimum number of moves that we are easily able to reach the destination. So let's see, we'll do one thing. First of all, I am going to fill the second jug. Okay, now what I am doing, now I am transferring this 3-liter water from this jug to that jug. So it look like 3, 0. Okay, now I am again going to fill the second jug. So this become 3, 3. Okay, now what I am doing, I am transferring 1 liter water from this jug to that jug, because this size is 4 and this size is 3. Now I am transferring, I am going to fill the first one completely, so it become 4 and it become 2. Now just drop this water on ground. Now send this 2 liter to the first one. You can see you reach the destination with minimum number of moves. 1, 2, 3, 4, 5, 6. So in 6 steps you can reach the final solution. So total 6 moves required, and we can say that there are different ways, but that would be the way on which you can go from initial state to the final state, and this all are the intermediate states. Are you getting the point? Great. So I hope this video is clear what is the problem and what is the problem solving strategy in AI. So I hope this session is clear to all of you. Thank you so much. Bye bye. Take care.